So there is much more to the structure of constructible numbers than just their field axioms. Addition, subtraction, multiplication, and division are not the end of the story. There's one more feature that the constructible number field has that makes it special. That's the square root property. So the idea is if I have any constructible number k, I can construct the square root of k. This is a really cool construction. It's again going to depend on the similar triangles idea that the multiplication of constructible numbers is dependent upon. So here's how it goes. The idea is first I'm going to take that same unit length that we started our constructible numbers with and place it at the end of my k here along a straight edge. Then I'm going to draw a circle, the diameter of which is this k plus 1. Right? So this is one big circle centered at the midpoint of the joining of these two lines. And then right where k and 1 meet, I'm going to construct a perpendicular bisector by first drawing a circle and then two larger circles, and where they intersect, I'll have a perpendicular bisector to that k and 1 line right there. I'm going to extend that all the way up until it meets the circle that we just drew on the top. Then I'm going to connect the two endpoints of the diameter to that point that we just identified on the upper arc of the circle. I can do that just using a couple of straight edges. Now, let's take a look at what we have here. We've got an altitude for this big triangle that I'm going to claim is r. In other words, the square root of the k length that we see in the lower right here. So why is r going to be the square root of k? Well, let's take a look at the angles in these triangles. On the one hand, we have potentially three different angles here, A, B, and C. Now, the C angle, by construction, was 90 degrees. But, according to the circle theorems in geometry, this angle up here at the top, where our green and our pink line meet the upper arc of the circle, that's a 90-degree angle. According to the circle theorems, because the circle theorem guarantees that the inscribed angle is going to be half that of the circumscribed arc that we have here. And the arc is half of a circle, 180 degrees, and so that angle up there at the top is 90 degrees. But then that implies that A and B must be complementary angles to one another. And if A and B are complementary angles, then that means we can also find A and B up here at the top as well. So what we end up with are several triangles here that are all similar one to another. And so we're again in that situation where now we can make an argument about a constant ratio between the lengths of the sides of those similar triangles. What does that look like? Well, let's take the sides of two of our triangles that are opposite in angle A and the sides that are opposite in angle B. Now, according to the principles of similar triangles, those sides should stand in the same ratio one to another. So if I pick the triangle on the left here, the side opposite A has a length of r and the side opposite B has a length of 1. If I instead pick the triangle on the right, then the side opposite A has a length of k and the side opposite B has a length of r. And so all told, we have this proportionality between the lengths of those sides whose cross ratios give us the equation r squared is equal to k. So indeed, with our compass and straight edge and nothing else, we have managed to construct the square root of k. So that's something really special about the constructible numbers. It tells us whenever we can construct any number, we can also construct its square root. So how do we build up the field of constructible numbers, beginning from the rationals? First of all, we know for sure that all of the rational numbers are constructible. Why? Because we can construct 1 by definition, and then we have addition, subtraction, multiplication, and division, and those operations are all commutative. Well, addition and multiplication are commutative, and so any number system that includes 1 and is closed under those operations and make it into a field will at least contain the rational numbers in it. So definitely every rational number is constructible. But then more is true according to our square root property. If I can construct any rational number, then I can also construct the square root of that rational number. This is according to the slide that we just saw a minute ago with the inscribed angles inside of a circle. So as an example, if I take the rational number 5, I can construct the irrational number square root of 5. And that's going to belong to what we might call this first level on our list of constructible numbers. We'll call it K1. But here's the wrinkle. We don't just get square roots of rational numbers, pure square roots of rational numbers. Because we also have addition, subtraction, multiplication, and division, in other words, because our constructible numbers form a field, not only can I construct the square root of 5, but I can also construct, for example, 4 minus the square root of 5. Why? Because 4 is constructible, and radical 5 is constructible, and I know I can subtract constructible numbers. So 4 minus radical 5 is also something I should be able to construct. The idea is that the elements that belong to this first level, which we're going to call K1 here, they're not just pure square roots, but they're potentially the sums of square roots of rational numbers with rational numbers themselves. For example, a 4 plus negative radical 5. And one of the ways we can relate these back to the rational number field itself is to rationalize it. This is that skill from high school algebra that's totally underrated and undermotivated at the time. But here's what we can do with it now. If I want to make this number, 4 plus negative radical 5, back into something that's rational, what should I do? I should multiply it by what we used to call its conjugate, right? We take the square root part that's not rational and we flip the sign on it, and after I do that, difference of two squares shows me that that product is equal to 9, which is a rational number again. So it really just kind of takes us one step to rationalize one of these numbers in K1 and get it back into the rational field Q. But we also have other square roots that we could potentially add into the puzzle at this first level. What about 2 square root of 7? It's the square root of the rational number 28. If I decide to add that on to this puzzle, then how would I rationalize this? Because it has two independent irrational components to it. It turns out that in order to rationalize a number like 4 minus radical 5 plus 2 radical 7, we have to multiply it by several different flavors of conjugate before it becomes rational again. In other words, I can flip the switch on the radical 5 portion, as we do over here, but I can also independently flip the switch on the 2 radical 7 portion, as we've done in these examples. And every possible combination or permutation of flipping those switches, taking the conjugate of one of those pieces, taking a conjugate of the other, is going to give me a different conjugate. And I have to multiply all 4 of those together before I get something that's rational again. If I just multiply the first pair, I'm going to get 4 minus radical 5 squared minus 28. If I multiply the third and the fourth here, I get 4 plus radical 5 squared minus 28, neither of which is rational. But by the time we multiply all of those together, so simplifying the arithmetic we have inside of each, and then multiplying, then we do get something that's rational, negative 271. So the concept of a conjugate, as we'll see, actually becomes more interesting and more complicated the more independent irrational elements that we have. Because square root of 5 and square root of 7 were independent from one another, each of them has its own notion of what a conjugate should be, and we have to take all of those conjugates into account before we land back into the rational field. But of course, the constructible numbers are also closed under square root, and so the square roots of those K1 elements are also constructible. We'll say that they belong to K2. We can keep going with this construction. 4 minus radical 5 plus 2 radical 7, if we take its square root, we're also going to get something that's constructible. We could also find the pure fourth roots in K2. So for example, if we take 15 in the rationals and take its square root, it lands in K1. The square root of that, which is the fourth root of 15, will land in K2. So we can construct fourth roots because we can construct square roots of square roots. And of course, we can still keep going. The square roots of those will pick up the pure eighth roots just by taking the square root of the square root of the square root. But then because of the field properties, addition and subtraction, we also have a lot more different kinds of elements in these sets here as well. And so we think of the set of all constructible numbers as the set of everything that we could get somewhere along this line, everything we can obtain at one of the levels in this list. But it's not an infinite process of going all the way up. In other words, no constructible number will be arrived at an infinite sequence of compass and straight edge constructions. After all, by definition, constructibility requires a finite sequence of compass and straight edge constructions. So it's everything that we can obtain at some finite row in this list. Every element which belongs to K belongs to some K sub j for a finite number j. This is an example of a more general construction in mathematics. It's called a direct limit. It's not something we're going to talk about in our class, but in a upper level algebra class, such as at the graduate level, you'll do some more work with direct limits. This is just kind of a taste of a more general construction. So how are we going to characterize these things? What is it that makes a constructible number constructible from the point of view of algebra and field theory, and not from the point of view of geometry? Here's the idea. Take the square root of 5, for example. How far up in the tree, the ladder, did we have to go before we found square root of 5? We just had to go up to K1. Why? Because it was the square root of a number that began its life as rational. And so because it's only one step removed from the rational numbers, we can find a polynomial equation with rational coefficients that radical 5 satisfies, and the degree of that polynomial is 2. T squared minus 5 is equal to 0 is what we are going to call the minimal polynomial of the number square root of 5 over the rational number field. What about the more complicated example, 4 minus radical 5? This wasn't directly the square root of something from Q, but can we find a polynomial equation with rational coefficients that 4 minus radical 5 satisfies? Sure. According to the conjugate roots theorem, the other root that this polynomial equation will have to have, apart from 4 minus radical 5, is 4 plus radical 5. And now from the knowledge of these two roots, we can construct a polynomial equation that both of those roots satisfy. All we have to do is use the sum and product theorem. The sum of these two roots is equal to 8. The product of these two roots is equal to 9. So according to the sum and product theorem, a polynomial equation that has 4 plus minus radical 5 as roots is t squared minus 8t plus 9 is equal to 0. That's the sum and product theorem. So in fact, here we have again found an example of a polynomial equation with rational coefficients having degree 2, so it's quadratic, that has 4 minus radical 5 as a root. That's why 4 minus radical 5 belongs at that first level, because it's only a quadratic equation away from the rational number field. Alright, so how do we get things that are more complicated, like this 4 minus radical 5 plus 2 radical 7? Remember we said that because there are two different independent irrationals as a part of this one object, the number of conjugates that we have goes up. We have actually 3 different conjugates for this number, just by flipping the switches on radical 5 and radical 7 independently of one another. So what polynomial equation with rational coefficients does it satisfy? Well, let's take the 4 minus radical 5 part and just imagine that that belongs to k1, as we were saying a moment ago. Rather than trying to leap all the way down to the rationals, let's see if we can find a polynomial whose coefficients belong to k1 that is satisfied by this number, 4 minus radical 5 plus 2 radical 7. According to the conjugate root theorem again, the other root that has to be satisfied by that polynomial is 4 minus radical 5 minus 2 radical 7, so one of the conjugates. And using the sum and product theorem one more time, we can find the coefficients of a quadratic that will have both of those numbers as the roots and whose coefficients belong to k1. So these belong to k1. And the minimal polynomial over k1 for these two numbers, 4 minus radical 5 plus and minus 2 radical 7, is the one that we see down there. But again, we don't just want those two. We want to get all the way back to the rationals, and in order to do that, we need to include the 4 plus radical 5 versions of these numbers as well. And in order to do that, we can use the sum and product theorem one more time to find that there's another quadratic polynomial whose coefficients are in k1 that will have those two as the roots. And the sum and the product will be those, 8 plus 2 radical 5 and negative 7 plus 8 radical 5. And according to the sum and product theorem, this polynomial equation, then, has those two other conjugates as the roots. Now, we want to take the leap all the way from k2, where we think these numbers live, all the way down to q, the rational number field. In order to do that, we need a polynomial with rational coefficients that has all 4 of those numbers as the roots. In order to find those, all we have to do is to take these two quadratics and multiply them one by another. Because the field, the ring of polynomials with integer rational coefficients is an integral domain, we know that if we multiply these two together and set them equal to 0, that each one will in turn have to be equal to 0, and each one of them is going to give us 2 of the different roots that we wanted. So we'll do all the arithmetic, and I'm going to spare you the gory details on that. But when we do all of that arithmetic, it turns out that we do get a polynomial whose coefficients are all rational. In fact, they all turn out to be integers. By the way, recognize this number, negative 271? We've seen that number earlier in our presentation here. This number turned out to be the product of all 4 of these roots. So there's some food for thought, and it's definitely not an accident. But the point is, again, that this is a polynomial with rational coefficients whose solutions, whose roots, are all of our 4 minus radical 5 plus 2 radical 7 and all 3 of its conjugates. And so that, then, is the minimal polynomial equation for those numbers over the rationals. And we can say that this, as an element of k2, has a 4th order over the rationals. So it lies in a quartic extension of the rationals and not a quadratic extension of the rationals. We could keep going. Those elements we find in K3 are going to have 8th order over the rationals. Those that we find in K4 are going to have 16th order over the rationals, and so on and so on. And so we arrive at the big finish of this. How are we going to characterize constructible numbers? Numbers are constructible exactly when they have an order over the rationals, which is a power of 2. So to unpack that a little bit, we say that a complex number is constructible if and only if there exists an irreducible polynomial. So we can't be able to factor this polynomial in any way. That's non-trivial anyway. That polynomial should have rational coefficients, and the degree of that polynomial should be a power of 2. So as an example of why we need irreducibility, the square root of 2 is a constructible number, as we showed directly using geometry. But on the other hand, it's a root of the polynomial t cubed minus 2t, whose degree is not a power of 2. But we still want radical 2 to be constructible, so how do we resolve this tension? Just by observing that t cubed minus 2t is not in fact irreducible, we can factor it into t times t squared minus 2. And that portion of that factorization which has the radical 2 as a root, t squared minus 2, this is an irreducible polynomial, and its degree is, in fact, a power of 2. So we really need that irreducibility hypothesis in order to make this work. Otherwise, the square root of 2 is not going to be a constructible number, and we can't have that. So then it's the power of 2 that takes center stage. Why do we need that power of 2 there? In the next video, we're going to look at more or less a proof of how the constructible number theorem operates. We're going to prove by induction that the process that we started by building up K1 and then K2 and so forth actually leads us to all the constructible numbers, and every one of them is going to have a degree over Q which is a power of 2.